It was an honored second when the Andromeda cloud transformed into the Andromeda Inestimable Framework. The James Webb Telescope has perceived 6 universes that exist a portion of 1 billion years after the colossal blast. This is impossible when you really look at the night sky. A pinpoint of light, when broadened, gives you one of these photographs from the Webb Space Telescope. It was an honored moment as the Andromeda cloud changed into the Andromeda world. For a really long time, our cognizance of the Andromeda world was confined to basic discernments. At any rate, with movements in development and the presentation of the James Webb Space Telescope, our appreciation has developed limitlessly. Now, things are going to change as the James Webb Space Telescope has recognized upsetting signs coming from the Andromeda universe. These signs have sent shock waves through the academic community, leaving stargazers both inspired and curious. Yet what unequivocally do these signs mean, and why are they causing such an uproar among space specialists? Join us as just 2 minutes earlier the James Webb Telescope shut down, directly following getting upsetting signs from the Andromeda Vast Framework. Previously, we could see far beyond our eyes into the universe. Cosmologists trusted the Milky Way to be the whole universe. This shortfall of information was essentially because of limited development for seeing different infinite frameworks and individual stars. In any case, everything changed when we found the Andromeda world. It filled in as our first piece of information that the universe extends far beyond the Milky Way. In the 17th century, Galileo Galilei's initiating work with telescopes revealed the Milky Way's conspicuous nature. He saw that the Milky Way had different stars, testing the winning idea of its specific importance. Everything changed in the 1920s when Edwin Hubble found faraway objects beyond the Milky Way using the Hubble telescope. Edwin observed that these sublime articles traveling through the universe were universes, not exactly the same as the Milky Way. One of the frameworks was the Andromeda world, or M31. While this was when we first saw the Andromeda world through a telescope, Persian cosmologist Abd al-Rahman al-Sufi first noted it around the 10th century. With advancements in the 20th century, space specialists could see and sort out the genuine substance and exemplification of Andromeda. It is a hazy cloud containing a gigantic universe of stars. Like our Milky Way, our limitless neighbor is around 2.5 million light-years from the Milky Way. Since its exposure, the way we focus on Andromeda has altogether progressed. We have moved from ground-based discernments through telescopes to space observatories like the Hubble and the James Webb Space Telescope. Every movement in development has taken us higher than at any other time, helping us understand the mysteries of the Andromeda universe. We currently have more information into its composition and structure, making Andromeda a benchmark for thinking about the development and advancement of universes. This has uncovered more insights into the greater working guidelines of the universe. Scientists believe that to have a superior understanding of our universe and the Milky Way, we ought to think about the relationship between Andromeda and the Milky Way. This is especially apparent given that the two frameworks will undoubtedly collide in around 4 billion years. While studies and assessments have progressed, the James Webb Telescope has recently received an upsetting sign from Andromeda. This troubling sign baffles scientists, prompting inquiries regarding its cautious starting and possible implications. The James Webb Telescope's high-level sensors have recognized phenomenal development right inside Andromeda. The sign sent back to analysts shows results that contrast entirely from past insights, captivating scientists in general. The sign illustrates huge cycles happening inside the universe, potentially associated with its truly gigantic black hole or previously concealed events. Strikingly, one of the latest discoveries illustrates that Andromeda's mass may be a great deal more significant than that of the Milky Way, reshaping how we could decipher both astronomical frameworks. The James Webb Telescope has also provided detailed pictures and spectra of Andromeda, revealing the development of new stars and their compound designs. This new data is critical for grasping vast development and possible conditions for life. Additionally, the data from the telescope suggests extended development in Andromeda's dynamic core. This has eventually impacted its surrounding environment and is expected to shape its future development. By examining the gravitational effects on stars inside Andromeda, specialists gain insights into the scattering of confusing dark matter throughout the immense framework. Hopefully, this helps our perception of its impact on the components at play in the universe. Sorting out dark matter and its effect on the universe is one of astronomy's most conspicuous questions. Recent forward jumps by the James Webb Telescope have inspired various examinations. As scientists explore the insider realities of Andromeda, we currently learn about the framework's past and future. So, what have we learned about the Andromeda world through various examinations? Andromeda has shown imperative characteristics that set it apart from various universes spread across the universe. Its sheer size commands thought, with late assessments suggesting a breadth crossing around 220,000 light-years. This figure makes it one of the largest vast frameworks in the neighborhood group, much more significant than the Milky Way. This immense extension adds to its mass, including a normal trillion stars, surpassing our galactic framework in stellar count. Research also sees the framework structure as captivating. Not by any stretch of the imagination like a typical winding framework, Andromeda has an enlarging core and a thick center encased inside rings of buildup and gas. This is undoubtedly a rich ground for non-stop star development. Such features show a dynamic universe made by steady processes shaping its advancement. Among its numerous components, one of specific interest is its core, characterized by a two-crease zenith release, showing the presence of a supermassive black hole, unlike that of the Milky Way. This offers critical insights into the nature and activities of these enormous matter-eating openings. The Andromeda world is also encircled by a halo of sublime debris, involving stars, planetary and globular clusters, spanning numerous gigantic quantities of light-years in breadth. This colossal covering tells an exciting organized story of the world's intriguing start and history. The 460 globular clusters tracked down in Andromeda similarly offer information into the arrangement of stars at their outset stages, giving a reasonable explanation of the advancement of star gatherings and the early development of the universe. In figuring out the secrets of Andromeda, astronomers are the slightest bit closer to understanding the massive congruity of dark matter. However, one question remains. How do they represent its astounding nature and the role it plays in the components of vast frameworks? Andromeda boasts another undeniable component: its satellite universes. Its crown structure contains over 20 more subtle immense frameworks, and some of them are undergoing streaming, losing their stars and gas. This cycle incorporates a greater grandiose framework, pulling in and demolishing adjacent minor, inestimable frameworks. This exhibits the dynamic nature of immense development and describes how universes create and associate with one another over the long term. So, what does the future hold for the Andromeda framework? The shape and direction of its development entrance fascinates cosmologists, as well as those attempting to grasp the universe. The opportunity of its encouraging from a twisting to a ring universe is central to Andromeda's headway. Confirmation centers to a connection that could initiate other captivating mixes, perhaps from enormous effects or close relationships with various universes. If Andromeda is indeed moving toward this path, it suggests that it has experienced various associations with other astronomical frameworks since its first encounter with the world. Ultimately, Andromeda's future depends upon the unpreventable accident with the Milky Way. As shown by these models, the effect is projected to generally happen 4 billion years from now. The outcome of such an impact is the presentation of a new world from these two giant celestial bodies. However, it is crucial to note that the effect is a characteristic piece of vast progression. Due to the gigantic distances between the universes, this infinite crash is most certainly not an immediate, quick impact. After the effect, the two infinite frameworks would be significantly modified, outlining new shapes and associations. The correspondence of their gases and debris will work up new rounds of star creation, inciting an immense presentation above as the mixing objects shimmer brilliantly. Ultimately, such a colossal event will result in the development of a lone, round universe. This kind of effect isn't uncommon, as the universe has a long history of such events. However, our immediate interest makes it a significant event for us. Additionally, the potential crash of the exceptionally tremendous black holes at the center of the two universes adds more intrigue to the grand spectacle. This suggests a complicated and significant nature of tremendous advancement. The union is expected to convey impacts for issues being absorbed by the black hole, which will generate vast radiation. This connection offers huge data about how grandiose frameworks move throughout their life cycles and how black holes impact this development. Nevertheless, it raises a significant question. What will happen to our nearby planet group after this combination? It could lead to a total destruction of the nearby planet group. The nearby planet group's course and conditions could be changed dramatically. This suggests possible orbital changes or even ejections from the newly formed grandiose framework. To understand this mechanism, scientists can concentrate on the size of relative events happening and contextualize the possible fate of our own universe. It is crucial to grasp that an accident between stars is a remarkable event in space, due to the immense intergalactic distances. However, the gravitational disturbance could agitate stars' stable orbits, causing some stars, including our Sun, to take a different path. Such a change could fundamentally alter the climate on Earth. Perhaps the most essential change individuals could experience is moving farther from or closer to the Sun. This could lead to either warming or cooling influences. A hotter climate could make ice caps melt and sea levels rise, while a colder one would incite another ice age. On top of that, the computation of such a scenario could hinder radiation levels reaching Earth, creating even more challenging conditions. The Milky Way and Andromeda vast frameworks are headed for a monumental effect, an event that will reshape the infinite landscape. This influence, estimated to occur in around 4 billion years, will be one of the most critical events in the universe's timeline. As the two universes draw closer to each other, their mutual gravitational attraction will initiate a staggering dance of tremendous forces. The accident isn't a direct impact but a continuous mixing process. During this cycle, the astronomical centers will eventually combine, inciting the development of another combined grandiose framework. In the initial phases of the accident, interactions between the vast plans will trigger remarkable star formation. The gravitational agitation will compress interstellar gas and debris, igniting new star births. This starburst event will create an explosive show of dazzling fireworks, with baby stars illuminating the merging universes. The gas and debris clouds mixed by the accident will shape thick nebulae that enable star clusters, adding to the visual magnificence of the cosmos. As the accident progresses, the components of the enormous frameworks will shift continuously. The Milky Way's winding arms and Andromeda's relative growth will disrupt, causing significant changes in their magnificent orbits. These disturbances will provoke the formation of new astronomical plans, for instance, streaming tails and surges of stars. The final result will be a lone, more massive, curved world, another tremendous component born from the union of the Milky Way and Andromeda. The examination of astronomical effects provides critical insights into the existence patterns of universes and their impression of other infinite framework combinations in the universe. It offers a brief glimpse into what could happen when the Milky Way and Andromeda collide, for instance, the merging of universes like the Andromeda galaxies or the colliding systems of NGC 438 and 439. These insights help astronomers predict the future evolution of our own infinite framework collision and understand the diverse processes involved. The accident's impact on individual stars and planetary systems will be less devastating than one could expect, yet the gravitational interactions will change their orbits. The enormous distances between stars imply that rapid cosmic collisions are rare. However, the planetary group's position and trajectory within the new infinite framework could be significantly altered. This shift could prompt changes in the planet's orbit and climate, potentially impacting the habitability of our planet. The merging framework will also have critical implications for the massive black holes at the centers of the two astronomical frameworks. The Milky Way's black hole, Sagittarius A*, and Andromeda's black hole will eventually merge to form a much larger black hole. This merging will be accompanied by the release of enormous amounts of energy as gravitational waves and radiation. The examination of these phenomena will provide significant insights into the behavior of black holes and their role in the structure of grandiose frameworks. Despite astronomical effects, the evolving types of grandiose development continue to enhance how we could interpret the universe. The advent of new space observatories and telescopes has transformed our ability to observe far-off frameworks and galactic features. Instruments like the James Webb Space Telescope, with its high-level infrared capabilities, have revealed previously hidden insights about the universe. The ability to look through vast clouds of gas has prompted discoveries about the formation of universes, the nature of dark matter, and the conditions for life. Radio telescopes like the Very Large Array and the Square Kilometre Array are expanding our knowledge of the universe's development. These telescopes detect radio waves produced by distant frameworks, pulsars, and other celestial objects. By focusing on these radio emissions, astronomers can explore the properties of magnetized gas clouds and the distribution of dark matter. Gravitational wave observatories such as LIGO and Virgo have opened a new window into the universe. These observatories detect ripples in spacetime caused by events like black hole mergers and neutron star collisions. The examination of gravitational waves has provided insights into the dynamics of compact binary systems, the nature of black holes, and the fundamental properties of gravity. The advancement of new observational techniques and data analysis methods is also playing a critical role in enhancing our understanding of the universe. Machine learning and artificial intelligence are being used to analyze massive amounts of cosmic data, identify patterns, and make predictions. These advancements are helping space specialists describe grandiose frameworks, detect exoplanets, and study the evolution of celestial systems. The examination of exoplanets and their potential habitability is another exciting frontier in cosmology. The discovery of Earth-like planets in the habitable zones of distant star systems raises the possibility of finding extraterrestrial life. Missions such as the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, have identified a remarkable number of exoplanets, some of which have characteristics similar to Earth. Future missions will continue to investigate these worlds and search for signs of life. The examination of galactic expansion, dark energy, and the accelerating evolution of the universe is providing answers to fundamental questions concerning the origins and fate of the universe. The exposure of dark energy, a mysterious force driving the universe's expansion, has reshaped how we interpret cosmology. Research into these phenomena aims to elucidate the nature of the universe's evolution and its ultimate destiny. In summary, the impending collision between the Milky Way and Andromeda represents a crucial moment in the universe's development. The merging of these two galaxies will reshape their structures, trigger intense star formation, and lead to the formation of another massive world. Advancements in cosmic development and observational techniques continue to enhance our understanding of vast phenomena. The examination of astronomical collisions, dark holes, and galactic expansion provides valuable insights into the potential of the universe and its ongoing evolution. As we investigate these cosmic events, we gain a clearer appreciation for the dynamic and ever-changing nature of the universe.